right, let's get this thing started. Oh, or not.
There we go.
Ah, that's better. All right, let's start with a short introduction. Who are we? My name is Dane Nilsson.
I'm Henrik Stroth.
We work for a company called Yubico. We make these hardware security devices that plug into your USB port, and they're used for two-factor authentication. They're very durable, they're waterproof, they contain these secure element chips. They're used at Google, Facebook, Microsoft, just to name some of our customers. The company was founded in Sweden. We now have offices in the US and England as well. We are very open source friendly. Please go to this page if you want to see some of our software projects. Pretty much everything is open source, available on GitHub. We have software and libraries for a lot of the things, especially what we're going to be talking about tonight.
And maybe we should mention all the links that you're going to see in these slides. You don't have to write them down, because we're gonna share a link to the whole slide set later.
Yeah, so there's one link that you do need to remember, which is the one to the slides, but that's like the one link to rule them all.
Yeah, I'm going to tell you when to pick up your phone and type, okay? And also questions, maybe.
Yeah, okay, so I think the way we're going to do questions is we're going to save the big questions until the end. If you have a question that's like, what was that thing on the, I didn't understand what that thing on the slide is, or something that actually pertains to the very slide we're talking to, then we can do like quick questions, to clarify the actual presentation. But if you have questions like, okay, well, would it be possible to do this, or how would I go about doing that, then save that for after, because that helps us kind of keep the flow of things going.
Yeah.
So our devices support a bunch of different protocols. We're not here tonight to talk about all of them. We're going to focus on one relatively new one, which is called U2F. And with that, I'm going to let Henrik explain the problem.
Yeah. So how many have heard about U2F before this? Wow. Oh my God. Okay. That's great. The problem, this is probably a familiar problem. Passwords. Username and passwords, the same story. They are being reused. They're being phished and man in the middle. They're being keylogged. And almost the worst thing is that users choose bad passwords in the first place, and then they reuse the bad passwords. Probably you know this, and you might say, didn't we solve this already? Maybe you have some kind of two-step verification, two-factor authentication, multi-factor authentication. It's called different things in different places. So let's have a look at what exists today and has existed. Smart cards. These are the things that, if you're using a Swedish bank, you probably have used a smart card. Maybe some of the banks. They have a few issues. You have to have a separate reader plug into your USB port. You have to have drivers. You have to have middleware. You have to, well, it costs quite a lot to let all your users, to buy these readers and things for all your users. And if you have two banks, then you have two readers and two smart cards. We also have SMS, which works like an email loop, but an SMS loop. So you get a verification code sent to your phone. And since only you have the phone, it's 100% safe, secure. No, but seriously, there are a few problems there. There's coverage. What if you're abroad? What if you're not in Stockholm? Or, I mean, out in the woods? What if? Yeah, there's a few problems. There's delay. There's no quality of service in SMS. There's cost. The cost to send SMS is a battery issue. You want to be able to access your accounts regardless of battery status on your phone, probably. Then we have OTP devices. So OTP means one-time password. So it's essentially a short code, which is your additional password for today or for this 30 seconds or until we generate a new one-time password, right? How many have used some kind of one-time passwords, for example, on your phone? Wow, OK, great. I guess that most of you have been using the ones on your phone. They also have a few problems. But more importantly, all of the existing technologies share some major problems. And that is the user experience. The user experience is not very, very good when you have to look up the code for this specific site or have the specific device for this account and then retype it before it switches to a new code, right? It might not be a big deal for you, but I assure you that it is for most users. It's a hassle and hard to understand. Even if it's easy for you, it might not be the type of thing that you want to do often. It adds friction. So maybe you're fine to log into Gmail using this and then click remember me for 30 days. But maybe you wanted to have some kind of authentication if you press delete all my emails. If your child does that, maybe you want to have some extra authentication while you're logged in. But you don't. Generally, we don't implement stuff like that. I mean, sites don't implement stuff like that because it's so costly, so much friction to authenticate. Another very important thing, very important flaw is all of the technologies that I mentioned, all the existing technologies are phishable.
Not smart card. Sorry.
Smart card. Well, yeah. That's debatable, I guess. But so phishable, what does that mean? It means that you fool someone to enter their credentials. And their credentials might be a password, might be a one-time password. So is it harder to phish a one-time password than a password? If I present you now with Google login page, my fake Google login page, or my fake Microsoft login page, is it harder for me to add another field that's called enter your one-time password here? No, it's not. The only thing that makes it harder for me is that password will only be valid for 30 seconds. So how long is 30 seconds for an algorithm, right? It's a very long time. So essentially, no phishing protection at all. And this is being seen by a lot of big web service providers and such as Google, seen a lot of successful attacks using phishing. And the same goes for man in the middle. Do you want to explain man in the middle?
Man in the middle, kind of related to phishing, is when you think you're connecting to a server, but your connection is going via some probably malicious third party that might be snooping in on your requests or modifying them. In which case, you think you're transferring 100 SEK to my friend Henrik for dinner last night when I'm actually transferring all my funds to some account in offshore holdings company somewhere. SSL is supposed to protect us from this stuff, but it's not always 100% there either, since CAs accidentally mess up and issue certificates for sites that they shouldn't, and things like that.
Mm-hmm, mm-hmm. Also being seen in the wild all the time.
Superfish was basically a man-in-the-middle attack against its users. It was happening on the computer, but still,
yes,
same thing.
Yes, very true. Lenovo Superfish, if you can recall. Yeah, that was fun, right? OK, so and also I want to mention phishing is a big deal. Let me assure you, phishing is a very big deal. Over 90% of hacking attacks begins with phishing, and then they just take it from there. It's always going to be someone in your organization that you'll be able to phish, if not most of them. And there's different kinds of phishing. You can do, these kind of lazy, kind of just throw something on the wall and see what sticks phishing. You don't have to be very detailed when you write the email, because someone's going to fall for this. Or you can do what is called spear phishing, when you do some research about you, and then I know who you work with. I know, I craft an email from your boss. I know what you expect to get from him, blah, 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 stuff like that. Then it's really scary. OK, so U2F, on the other hand, tries to solve this problem by making the user experience both for registration and authentication, just a touch of a button. There's no code to enter. It's not phishable. And it's got man-in-the-middle protection as well. So trying to mitigate all of those three big issues. And as a bonus, there's also a few other good things. Well, there's no batteries or drivers needed. It's a one-device thing. So you got one device, but you can use it on any number of sites. And it's an open standard. It's standardized by something called the FIDO Alliance, which Google is a leading member, a board member, and Microsoft and Yubico and others. And there's in total 200 member companies or organizations. And just going to show, this is slightly hard to see, but just going to show this is the use case that we have been talking about, and we're going to talk about mostly today. It says enter name and password, then insert key and touch button, done. USB, touch the button. That's the basic use case. But it can also be done, since it's called universal second factor, that's what U2F stands for. You could also you can identify yourself to the device by some kind of biometrics. Pick and choose whichever biometrics you want. Or you can have, there's other transports than USB. There's BLE, Bluetooth Low Energy, and there's NFC. So you could, if you don't have a USB port on your smartphone, a regular sized USB port, which most people don't have, then you can just tap your device against your phone or tablet. So, yeah.
Yeah, so let's take a quick look at what this actually looks like in practice. Oh, it worked. Well, no, actually, I need to get the mouse here. So this is standard Gmail inbox. Well, it's not standard because it's actually Google Apps for our domain, but it's pretty much a Google account. If you have a U2F key, you can go to your account page. So now I'm just logged in with username and password. This page has recently been updated. But since I tried this out earlier today, I know exactly where all the stuff is anyway. If you go to signing into Google, and then under two-step verification, there's a little edit thing there. Okay, I have to enter my password. There. So you go under two-step verification. There's a tab called Security Keys. As you can see, I already have a phone associated here. But if I go here to Security Keys, there's a little Add Security Key button. And now, as luck would have it, I brought one of these with me. So I'm just going to insert that into a port there. Click on the register button. And now the little LED on the key starts blinking. So I touch that with my finger, and it says that it's registered. Great. Click on Done. And it's listed here. So we can see that I indeed have registered a key.
In Kungsholmen.
Yeah. So what's up with that, Google? Close that. So now, the difference now is if I log out and then try to log back in. Because I registered that security key, I'm now asked to insert it and touch the button. And since it was already inserted, the light just starts blinking. Touch it. And I'm in. OK, no applause, fine. All right, let's see. Can we get back to? That was a joke. I wasn't actually expecting applause.
All right. So now that you have seen how it works, I should tell you this deployed in December. The standard was done in December, so it was finalized, the FIDO U2F standard. But Google has actually used this for the last 2 years, or they started rolling it out internally 2 years ago, and gradually increased support for U2F. And now almost all applications internally at Google supports U2F. So since that is so, and since also Google, I've been told, loves statistics and to measure things, and maybe I have gotten some statistics from their internal deployment. So these statistics are made by Google, and they are comparing U2F. I should also say that U2F doesn't have to be our stuff. There's other vendors. There's like 8 different vendors of hardware.
Yeah, we just randomly choose pictures of our devices for
ourselves. Yeah, next presentation we do this. There will be another key here. No, but I'm just, it's an open standard. And we're comparing, or it's being compared to this, which most of you had used by raise of hands, which is called TOTP. Actually, it's not called Google Authenticator, but that's a TOTP client. OK, so support incidents were 70% fewer. That's good. Login times 53% quicker, which is really good. And also, when you think about it, some people that worked at Google might have been using TOTP before, right? Because it was an existing standard for a long time, but none had been using U2F. So that's a good review.
Yeah, everyone had to basically learn this new flow.
But still, it was much faster. Yeah.
And quicker compared to what?
Compared to so this is the average login times of U2F compared to using these time-based one-time passwords to log in as a second factor. So we always use our password or have our session remember a password or browser or whatever. Yeah, so that's what's being compared, because those were the two big ways to authenticate at Google at the time, at least. 53% quicker. And security incidents, I haven't heard any numbers. As usual, maybe a company don't want to share exact figures, but a dramatic decrease in security incidents compared to TOTP. So obviously TOTP isn't 100% secure, right? Because then you couldn't decrease the number of security incidents
dramatically. All right, so you guys are all sold on U2F now, right? You don't need me to explain actually how it works or what it does. You're just going to trust that it prevents all phishing and man-in-the-middle stuff. Or maybe I'm wrong there. Maybe I should go into the protocol design. I think I will, because I have the slides, so why not? First, let me just go over what the different parts are that we're going to talk about. So you've seen the key. This is the U2F device. It consists of a user action, which is the button that you press. That is to indicate that there's actually a physical user present wanting to initiate some type of action. It means that if you plug this into a compromised machine, it can't just start spitting out authentications without you knowing about it. There's also a secure element, which is the hardware chip that performs all the cryptographic operations, stores all the cryptographic secrets. Now that is certified. It's the same type of chip that's used in credit cards and things like that. They've been, they're supposed to be. I mean, even with physical access, there should be no way to actually extract any of the cryptographic secrets from it. And then lastly, there is the transport, which in this case is the USB port. So plug that into the machine, and that's how the machine communicates to the U2F device. Then you have your browser, which acts as a FIDO client. So we mentioned this was FIDO U2F, right? So FIDO client is the name of a U2F capable browser.
And maybe the reason we don't just say this is the browser is because, once again, it's a universal second factor protocol. It doesn't have to be a browser. It can be your Swing application, your smartphone app, or whatever. But we're going to continue to say browser, pretend it's all the web, because to not make it too abstract.
So the browser has the capability to talk to the USB device since it's running native code on the machine. Web pages can't talk directly to the U2F device. They have to go through the exposed API, which is the U2F JavaScript API. So those two parts kind of form the user side of things. And lastly, you have your web server that's running some type of web application. And to make that U2F aware, you plug in a library that handles all the server-side crypto, runs all the logic, and makes it really easy for you as a web developer to add support. So what's actually stored in the database there and what the U2F library does is kind of what we're going to go through now, I suppose. So we're going to kind of build up this U2F protocol. We're not going to start with the whole thing. We're going to build it like a basic protocol, then we're going to add more and more stuff on top of it until we have kind of the final U2F protocol. So what I'm showing you first isn't actually U2F. This is kind of the first building block. But before I start, could we get a quick raise of hands? How many of you are familiar with kind of the concepts of public key cryptography? Quite a few. I think almost everyone. Maybe I should have asked if someone wasn't familiar instead. But yeah, you generate a key pair that's linked. So you have a private key and you have a public key. You keep the private key private. You can give the public key out. For this usage, we are doing digital signatures, which means you need to have the private key to create a signature, and that signature can then be verified using the public key. And the basic flow of the operations here is just like I demoed it. So you start by logging into your account, whatever that may be, using your existing authentication mechanism, so username, password. Then you choose to register a U2F device, which kind of binds it to your user. And from then on out, every time you log in, you need to authenticate with that device. So we're looking at registration and authentication here. So this is a basic challenge response. Is this the right slide? No, I skipped one. There.
This
Okay.
is the right slide.
Yep. So you have your server. You're logged in. You say, I want to register this this U2F device. The server says, OK. It talks to the JavaScript API in the browser. Says, a user wants to register a device. The browser talks to the U2F device. Says, hey, I want to register. The device has a key pair, the private key, public key. It says, all right, here's my public key. That gets sent via the browser back to the server. And the server stores, OK, this user has this public key. Great.
So this would actually work as a authentication mechanism, right?
Well, when we add authentication to it as well.
Yeah.
Which we do now. Yeah. So authentication works this way. You start by saying, oh, this is my username and password. The server validates that. But then it sees that, hey, this guy has a U2F device associated. So it generates this challenge, which is just a big random number, sends it, again, via the browser. That gets sent to the U2F device, and the U2F device now uses its private key to create that cryptographic signature over the challenge. And then you send that signature back where the server, since it knows your public key, can verify the signature. And if it matches, then you've proven that you have ownership of the private key. So yeah, so that forms the challenge response protocol, which works, but it doesn't protect you against phishing and all that other stuff we mentioned.
Yeah.
So to kind of add that, we take advantage of the fact that the browser actually knows a thing or two about what the user's doing. So the browser knows the actual URL, and the browser won't be tricked by a number 1 instead of a lowercase l in google.com. To the browser, those are very different things.
Or google.accounts.com.
Sure. And it also, as long as you're using a TLS connection, the browser has the client-side state of that. So this thing that we call the channel ID is kind of state about that connection, which if you compare it to the state on the server, you can determine that there is no man in the middle possible. So the problem is, of course, if you just send that to the server and there's a man in the middle, they could change that so that the server thinks it matches when it doesn't.
So the first thing protects against phishing.
Phishing.
Because phishing is when someone tricks you into going to the wrong URL. And the second one is about man in the middle.
Like the server says. That is correct. So we're going to add this to the protocol now. If we look at just registration, we will be adding it here soon, but not quite yet. So instead, we're going to add it to authentication first. So here's our previous challenge response protocol for authentication. The green stuff is the new stuff that we've added. So the server still sends his challenge to the browser. The browser now, instead of just forwarding the challenge, takes a look at the page and adds information about the URL that we're on and the channel ID. And that message called C here is what gets sent to the U2F device and is signed by the private key. The browser gets that signature back and can now send both the message containing the challenged URL and channel ID, as well as the signature back to the server. And the new thing on the server here is that, well, the server looks at the URL and the channel ID, makes sure everything matches with what's on the server's end, and by doing so, eliminates both of these attacks.
Yeah. So if I'm a server at Microsoft.com, and I see authentication, finished authentication coming in, it's signed by the correct device, and the URL says Microsoft.com because the browser, not the user, the browser has asserted that the visited URL was, in fact, Microsoft.com. And I know that I'm a server. I have a set of URLs that I, as a server, know are, who I work for, where I serve my content from. I verify that. So
we protected against phishing and man-in-the-middle attacks. We also said that you can use a single U2F device with multiple sites. So to do that, for private, one easy way to do this would be, just give that same public key to all the sites I want to use this with. But for privacy reasons, we don't want to do that. Ideally, what we want is if I'm using the same key with 2 different accounts, one that has maybe my personal information, my bank or something, and another, let's say, some type of embarrassing site that I don't want people to know about, where I don't have my personal information, I just have fake stuff. If both of those sites are hacked and databases are leaked, there shouldn't be anything in those databases that could link me as a user to being the same person on the embarrassing site as well as my bank. So these need to be completely separate keys, so there's no linkability there.
There's no security issue here. It's just a privacy issue, right? Because there's public keys. But
yeah. So even if you do get my public key, it doesn't mean you can actually do anything with it. But yeah.
Except for embarrassment.
Yeah.
Right.
So let's look at registration again. so we said we don't want a single key pair. We want a new one. So we're going to actually generate a new private key and public key for each new registration. But that means we have multiple key pairs. So we need a way to be able to refer to a specific key pair, saying, OK, I want to log in here at Google. I need to use the key that was registered for Google. So therefore, when we send back a public key, we also give it this key handle, which is just an identifier. Say, OK, this refers to this key that I'm giving you now. When you want me to authenticate, you need to give me back this key handle. So what the server does is that it not only stores the public key, but it also stores the key handle for later use. But we also need to prevent keys to be used with the wrong site. So if I generate a key pair for google.com and give them the key handle for that, if that key handle somehow leaks out, I don't want evil.com to be able to send me that key handle and get me to sign something using Google's key pair. So for that, we introduced this thing called an app ID that basically identifies, it's the domain of the site. So during generation here, we feed in this app ID saying, OK, we're generating this key pair, and it is only valid for this app ID. So this is a key pair only to be used with Google. And the browser actually makes sure that the URL we're currently on is allowed to use that app ID. So if I go to evil.com and evil.com says, hi, here's my app ID, it's google.com. Well, the browser will then know that, no, evil.com is not allowed to use google.com as an app ID. So that's what we do to change registration. And to be able to accommodate that change in authentication, the server, again, just adds the app ID with the authentication message. It also adds the key handle saying which key to use. Those get added to the process into the device, and we can look up the proper key pair to use for the handle, and we check it against the app ID. And if everything looks good, well, then we sign everything and send it back.
So this is the key is just, or the device is just doing a key value store, basically, kind of lookup.
Pretty much, yeah.
So it gets the app ID, says google.com or microsoft.com, and then it picks the right private key.
Well, yeah, signs. From the handle, it gets the key, and then it makes sure, was this key actually for google.com?
Right.
And this is almost the entire protocol. There's one more thing to add, which is actually an optional thing. So servers can completely ignore this if they want to. And that's device attestation. Now, the reason we have this is since U2F is an open protocol, it's an open standard, anyone can manufacture their own U2F devices, which is a good thing. But you can also write your software implementation of a U2F device. And a software implementation will never be as secure as a hardware implementation that has a secure element. For a lot of sites, that doesn't really matter because it's much stronger than a username and password anyway. But if you're a bank, maybe you want to actually only allow certain types of devices, like only allow devices that have secure elements in them, or only allow devices that are from one of these 3 vendors, because those are the ones that we can trust.
Yeah, so the reason we have this, I mean, your bank doesn't have this because they give you a device, and that's a device that's tailored for them. You cannot use that device with anyone else. But the philosophy behind U2F is you bring your own authenticator in most cases. So you go to Pressbyrån or to 7-Eleven and just buy a U2F device, and then you connect it to whatever you want to. So that's why we kind of get into this attestation thing, because banks might want to restrict with which devices you use. Yeah.
Exactly. So the way we do that is, first of all, I mentioned that we were adding the phishing and man-in-the-middle protection to registration. We're doing that now, so that's where all this stuff comes in. This is, again, just the stuff that the browser knows about. We're adding a challenge for registration as well now, so it looks very much like authentication. And now, so during manufacturing, we insert this attestation certificate, which is a certificate that contains information about the type of device that it's contained in. And the device also holds the key for that certificate. And in the registration response, first off, we return the full certificate so that the server can look at it and see what it is. But we also use that attestation key to sign all the registration information. So that's the newly generated public key. That's the state of the browser for the URL and channel ID, as well as the challenge.
Why do we do that?
To protect against phishing and man-in-the-middle stuff for registration as well.
But why do we have to sign it?
So it's not modified if there's a man-in-the-middle.
Right.
So the reason we didn't do that until now is that the only thing we could have signed with was this private key. So a man-in-the-middle could have, changed the entire key pair and given us a new signature. Basically, we would be using this public key to verify the signature, which doesn't really prove anything. But instead, now we're giving it this attestation certificate and a signature. And a man-in-the-middle here could change out the attestation certificate, but then the device would no longer kind of match that, so we wouldn't get the expected device.
A certificate is, for those who doesn't really exactly know, it's essentially a public key with some metadata.
Yeah, and it's signed by a CA, so just like an SSL certificate.
Yes.
So in the case of our devices, these attestation certificates, they say, okay, this is a Yubico device of this type of model.
It's got a secure element.
Yeah, and here it's signed by Yubico's root certificate.
Yeah.
So if you trust Yubico, then you can trust the certificate, and then you can trust the signature.
But there's no like big central organization. It's not like FIDO Alliance are charging for attestation certificates or something. This is Yubico, for example, we do our own attestation certificates, and anyone can do it. If you do a software implementation in JavaScript, as someone has already done, then you just generate a certificate on your computer with OpenSSL or with anything, and off you go.
Yeah. So like I said, this is very much optional. I mean, you have to have some certificate, but it can be a self-signed anything certificate.
And we should maybe mention Gmail or Google accounts. They don't look at this. They accept anything. Yes.
How do you revoke your certificate? YubiKey, like device certificate, the one you issued inside.
Yeah. So so once you get this attestation certificate, the server needs to kind of choose if they want to trust it or not. So it's signed by our CA, which we publish on our site. We could also publish, revoked certificates. So you could have. I mean, this is an X509 certificate, which is the same type that's used in SSL, and there are mechanisms for.
If my key gets stolen, I have to contact Google.
Okay, no. So these are not unique to the device. This is just attesting. So that's a different issue. What happens if you lose your key? Let's save that until after. Okay. Yeah.
Please remember, it's a good question.
Yeah, I'll try to remember it as well.
Because everybody, fancy security, look, how many handles, but we forgot the revocation. Fuck.
Right.
Doesn't work it out.
Yeah.
Good question.
We'll say that. Okay, so we have this attestation. For most people, you might not want to care if you're, high security thing, or if you're, if you're a bank and you're issuing devices to your employees, you might want to make sure they're using the actual type of devices that you're giving them or something. So then you can look at that. And with that added, I think we're done with the protocol flow. So, Henrik, why don't we look at
yeah. Now for something slightly less technical. It's just programming. Okay, so what if you want to add U2F support to your website, or to your hobby project, or to anything, to your Android app? Do you have to read all these slides and read the specification? No. As with most technologies, there are people that have written libs for this, which are open source. So you can. It's not that complicated to use U2F, even though it does a lot of smart things, which I'm going to show you now. So if you are lucky enough, maybe, to use one of these frameworks, there are already plugins, or modules that you just plug in and then it works. So you don't have to do anything. It just fixes all the JavaScript and all the backend logic for you. So no surprises there. This list is growing constantly. Then there are some off-the-shelf solutions. So if you're, this is the usual deal. If you're a big company and you want to, buy support with, you want to be able to call someone in the middle of the night, and you want it to be just an easy REST API, and you don't want to store any even public keys, for example, then this is perfect. They've got different tiers, probably like free tier and non-free tier and stuff like that.
Henrik has no idea what he's actually talking about there.
I haven't tested any of those, actually. But there are a lot of implementations. What I have tested, though, is this, and written a few of these. So these are open source U2F libraries in various languages. There are even more languages, but they're not maybe mature yet. So I've just listed the ones I really like. OK, so let's pretend that you want to use one of these libraries. How complex would that be? Let's have a look at some code. So this is some kind of Python pseudocode. Keep in mind what Dane said. He said U2F is a challenge response protocol. So that means we need the server to generate a challenge. And we need, on the client side, in Chrome, for example, we need to tell the key to sign the challenge, to create a response. And then we need to send it back to the server. That's 3 steps. So I'm going to show you those 3 steps. So let's pretend we have an endpoint at our web server called the start authentication. And this is the function. And you get a username and password. What do you do with usernames and passwords? You verify usernames and passwords. And I wrote it in gray because that's what you always have to do, right? It doesn't matter if you're using U2F. This is the U2F part. So in this case, the user is already registered. We're looking at authentication here, but registration is very similar. So we already have a device registered for this user. Essentially, we have a public key and a key handle. So we look in our device store, which can be any store, key value store, your enterprise database, and we look for the registered device for the username that just authenticated by password. We got the registered device. We use our U2F library and call a method called start authentication, something similar. As a parameter, enter our registered device. So we got the public key, and then app ID, our home URL. Then we get a challenge. And then we store this challenge for future reference because we will later have to verify that the response matched the challenge correctly. So we need to call our data store again and just store it away, and then return this challenge.
Now, this challenge isn't the actual challenge that was shown in the previous slides that I showed, the string. This contains that, but it contains some other parameters. I mean, this is more of a challenge object that contains the key handle and app ID and stuff. So it's not just the challenge string.
Well, it will become clear on the next slide, I think. So we return this, and if this is the well, eventually we wrap this in some HTML, right? Because that's what you do on the web. You don't just serve challenges to people. You wrap them in HTML and JavaScript and stuff. So next, please. Thank you. So now we are zoomed inside our pretty HTML with CSS and stuff. And this is the vital part for U2F. This is JavaScript. And the U2F object you might not be familiar with. But that's what U2F supported, or browsers that support U2F have this object that you can use to talk to your U2F device. So you call the sign method. Sign, or you might want to call it authenticate. It's called sign. So you sign the challenge. And these are the three. These are the actual three strings that are contained in this challenge object that we got from the server. So we got the actual challenge string, and we got the app ID, and we got the key handle. So we just throw that into the device. Chrome will now append some other data to this before it asks the device to sign it, namely the things that Dana has been talking about.
The URL,
the
channel
URL,
ID.
Yeah, the channel ID, exactly. The phishing and middle protection. And then we just use this method, provide a callback. What happens now? What do you think happens if we run here? What happens for the user? Well, the user sees a flashing device and touches the device. Then when that is done, this callback gets run with a response from the device, basically a signature. And somehow we send that to the server. Choose your favorite way to send stuff to servers. And OK, so now we have generated a challenge from the server. We have sent the server to the device. We are sending it back. The final step would be then to verify that the signature, that the response from the device is correct. So let's pretend again that we have this finish authentication endpoint. So the first thing we do is we get the device response to the username. So we want to get, once again, we want to get this device handle from our data store so that we know which device are we actually dealing with here, which public key. And then we want to do the same thing for the challenge. Remember, we stored the challenge when we generated it, so we know what we asked, what question we asked, so we know if the answer is correct. And then we just let the U2F library do it all the crypto stuff. Oh, this was the challenge I asked this device, and this is the response it gave me. And by the way, this is the actual device we're talking about, and it's public key. And then if this doesn't throw some horrible exception, then you're good to go. Then you're done. User authenticated successfully. You can send back a cookie.
To reward the user.
To reward the user with a cookie, session cookie.
All right. So a common question we often get is, since we have a key pair for each account we register, how many user accounts can we support on a single device? Now, the thing about these secure elements is that they are made for security. They're not made for storing a lot of data. So a lot of them have very little data to actually, or very little space to store data on them. So the answer is lots, actually. Any number of key pairs can actually be stored on the device, stored within air quotes as well, because what we're actually doing is we're not storing anything on the device. This is not part of the U2F specification, but the specification states some similar ways to do this. This happens to be our implementation of how we do this.
Should we ask the crowd how many are familiar with the details of Bitcoin protocol? Is that relevant here?
Not sure.
OK, how many are familiar with the details of the Bitcoin protocol? OK.
Yeah, you have to be familiar with certain aspects. Let's forget that. How about a hash function? How many of you know what a hash function is? Yeah, a few more.
How many know what a HMAC is?
About the same. So yeah, a hash function is a one-way function. You give it some arbitrary input. It gives you a fixed length output, and it is irreversible. So given that output, there's no way to figure out what the inputs were. HMAC is just a certain type of hash that has a key as well, meaning that you need to have a secret key to be able to perform that hash. Now, during manufacturing of our U2F devices, first off, each secure element has this onboard random number generator that can generate random numbers. But we use that during manufacturing to generate this device secret that's generated on the chip. It never, ever leaves the chip under any circumstances, and it can't be extracted in any way. So that's there since manufacturing. What we do for registration is we get this app ID in from the server. We generate a new random number. We take the app ID, random number, and device secret, run them through one of these hash functions, and that gives us what we use for the private key. So instead of storing this, we depend on being able to recreate it at a later state. So anytime, if we have these 3 inputs, we can do that. We also use the same function, again, using the device secret, the app ID, but this time we use the private key instead of this nonce. And this gives us a new hash. This is used for verification. And the crypto we're talking about here is elliptic curve cryptography. And one of the details there is that, first off, any large number can be used as a private key. It's not like with RSA when you have to figure out these large primes and you have to do stuff with them. So basically any large number, so any output here is a valid key. And also you just need the private key to calculate the public key. So that's trivial. Of course, you can't go backwards. So we do this to generate a new private key. We also get this little MAC code that's used for verification. And when we send back the key handle and the public key, we build the key handle as the nonce, which is the random number we got, and we concatenate the MAC, which is this hash that we use for verification, and that is our key handle. Now, the server has no idea what that is. That's just a random-looking string. But it means that for authentication, when we're giving the app ID and the key handle, we just break that apart, and we get the nonce of the MAC back, which means we have all 3 inputs to recreate the same private key and public key, and we do the same thing for MACing. We compare that MAC to the one we got. If that matches, that proves to us that this key handle was generated on this particular device with this secret, and we have the private key to use for signing.
So even though I've seen this a lot of times, I always have to sit down and just stare at it to figure out how it works again. And so don't feel, disappointed or anything if you can't follow everything here. And also, additionally, this is not even part of U2F protocol. What U2F says is the device should be able to store a number of different keys for different websites, and it's up to the manufacturer or you as a software implementer of this device how to do it. So if you have a lot of memory, you can just this essentially what this translates into. If you would have onboard memory, onboard storage is just a key value store.
Yeah.
And we just have to make it really complicated because we don't have lots of onboard storage. Yes?
What they use for RNG?
For
RNG.
RNG. So the secure element, which we have a few different chips depending on which model, but they all have built-in random number generators.
It's part of the secure element.
Yeah.
Is it like thermal-based or is like something standard?
I'm not sure what the actual hardware implementation is, but it's.
No, I don't know either.
No.
But it's part of this standard secure element thing.
So it's black box for you.
Yes.
For us,
yes.
black box, yes.
Yes.
Ready?
Well, it's gone through all kinds of certification from whoever certifies those things.
I think it's. I think
it was the NSA or something. I don't know.
I think it's. I think you'll have hard time finding hardware such as credit cards and stuff that does have an open.
I happen to work with RNG, so I know what I'm talking about.
Yeah, I'm sure. Yes. Yeah, you're correct.
You're correct than we do about RNGs. So. All right, that would conclude the presentation for today, except for one more thing.
Yes.
Yeah.
So let's say I have a religious server with my key.
Yeah.
Hundreds of servers.
This sounds like a question that we take in a few slides.
Yeah,
okay?
it's like 2 more slides.
Yeah.
Sorry. So the one more thing is everyone here come up to us and get a U2F key that you can use for your Google accounts. We should mention these are brand new keys, and there's this. We actually didn't mention it in the protocol because it's not really that important. I mean, some of these things were slightly simplified just to make it easier, but there's a small bug in Google's server implementation where there's this counter that starts at 0 and increments for each signature. Google won't accept the value 0. According to the specification, they should, but they don't. So they've said they're going to fix it. We're happy to be here. Thank you, Google. We know they're going to fix it. This does mean that the first time you use this key, if you use it with Google, it's going to say login failed. But just do it again, and it'll never bother you again. It's a feature. Yeah, so we have instructions on how to add it to your Google account. If you don't remember the demo I just did, there's libraries, plugins, sample code, documentation. We have our own demo server where that doesn't have this bug, where you can you can just test doing a registration. You can test doing an authentication. It's going to show you some technical details about what's actually being sent. A lot of that is encrypted, so it's just going to look like random garbage, but it shows you kind of what you could see from the outside. So feel free to try that out. Thank you, guys. And I guess now we'll do questions.
Yeah. Thank you.